All right, well, it's that time.
Yeah, it's 10:03.
All right. So first of all, thank you guys all for coming and joining us today. We understand that in a fast-paced world, that time is our most precious commodity, and so the fact that you have chosen to share some of your time with us today means a tremendous amount to us. And we carry a heavy burden to live up to that responsibility that you've given us. And so our goal in this educational webinar that we're calling Behind the Bot, Inside the Machines Changing Our Daily Lives. Our goal is to help to educate people regarding the core technologies that exist behind this new emerging tech, to help alleviate some or demystify some of the common misconceptions of what automation and robots really are, and hopefully to illuminate an understanding of how you might be able to take advantage of these types of tools and devices in your own life, or even in your own businesses. So we wanted to extend a thank you for that. We appreciate you guys joining today. And so to get started, my name is Ryan Krajecki. I am the owner and branch president of RobotLAB Chicago. I am an industrial automation sales engineer, and I've been in the field for 28 years, which is hard to believe. I did start when I was 9, so I'm really not that old. But I've been in and out of a lot of factories, but generally I'm just a lover of technology. It really excites me, and we're happy to be able to share some of that with you today.
Right. And then I'm Andy Krajecki. I graduated from Rose-Hulman Institute of Technology with a Bachelor of Science in Optical Engineering. For those that don't know what optical engineering is, it is a discipline of physics that is tailored towards light and how light interacts with the environments, with our technologies. So this includes cameras, sensors, and laser technology. And then for the past 2 years, I was working with high energy laser systems that were conducting cleaning and rust removal type processes. And then through my work experience and then my personal experience, I've had in-depth robotics experience, whether it's installing 6-axis arms or installing our service robotics, and then also working on robotics teams in the past. So just wanted to give you guys that we have some experience with robotics, and we're very excited to talk about them.
So, considering this technology, I think carries with it, like I said, some preconceived notions of what robots are. We thought we'd go kind of just back to the basics of what a robot is. So we return to something Andy has probably never heard of before, but we call it the dictionary. And in the dictionary, a robot is defined by a device that performs complicated, often repetitive tasks. And then the second layer of that definition is a robot is a mechanism or device that is guided by automatic controls. Right. So one of the things that, Andy and I, when we were talking about getting ready for this seminar, was kind of thinking about robot and the word robot and putting it into its proper context. And so that we kind of settled on the idea of, instead of using the word robot at the beginning here, we're going to use the word automation. So at the end of the day, a robot is just a type of automation, and that is, where we take a technology and then we marry it with human labor, right? Mm-hmm. And we elevate the total productive output of that human by applying a piece of automation or technology. Right. So in the end, that's what a robot is. It's a much wider spectrum of a definition than I think most people are familiar with. But for our purposes today, this is what a robot is. So the term that we kind of use in the expression is robots are automated systems that perform tasks through guided controls. These controls can be anything as simple as engaging a water pump or controlling temperature, all the way to complex processes such as welding car frames. The field of robotics is used primarily at solving problems through a lens of efficiency, repetition, and cooperation with high-end electromechanically developed systems. I know, that's a mouthful, but our job here is to kind of take that statement and break it down into its simpler components. So, in addition to defining the word robot, what we wanted to do was to kind of talk about how we're already surrounded by automation today. And it's often overlooked, but humans have been increasingly involved in automation. This includes things like dishwashers, washing machines, ordering kiosks. I mean, ovens and microwaves are automation, right? You set a temperature, and if the oven is not at the temperature that you've set it to do, the oven increases the temperature to achieve your goal. So that's a piece of automation. For hobbyists, 3D printers are automation. CNC machines for the most advanced industrial automation, the world that I live in. Even computers and their programs are automation. Driver assist in your cars to self-driving cars and even video games. And additionally, the world that I live in here for the last 28 years, and a lot of people don't really realize this, I don't think, but a lot of the products that you use on a daily basis are made out of these type of manufacturing systems, and they're all around you. It doesn't matter where you live. In Chicago, where I've spent most of my life, I mean, there are hundreds and hundreds of factories that look just like this out in the automation space. So as we can tell, we are already surrounded by automation. You know, it's often thought that this is some new thing, and, you know, robots are new, but in reality, we are all living from, you know, off the benefits of automation and sort of are immersed in it at the same time.
Right, and we are so immersed with this technology, but where does it come from? How can we kind of describe the history of robotics from technological improvements that brought us to where we are today?
We thought a good thing was to kind of go down Nerdville, where Andy and I tend to live, and to talk about the history of what automation really is. And so, as we had mentioned, and we're going to kind of repeat this message quite a bit, that all automation really is doing is taking the productive output of a human, leveraging it with some technology to elevate the total productive output. Right. So, for example, the picture in the upper left-hand corner here is a picture of a textile manufacturing plant from the 1850s. And at the time, the U.S. military was looking for uniforms for people in the Civil War. Well, previous to this era, all clothes were hand sewn. Right, the material was cut, it was sewn together by hand, and then eventually you would end up with a garment. Well, this is where we begin to see how automation really interacts with the market. Given the scenario that we had with the Civil War, we had a much higher market demand for clothing than we had previously. Right. And the total productive output of people who knew how to sew was not large enough to meet that demand. So, as we're going to see through this process, clever engineers and designers came up with a system that automated the plunging of the needle. And as a net result, whereas one person maybe could make a garment in half a day, now one person with the use of automation can now make maybe 5 garments in half a day or 10 garments in half a day. So we take the normal output of a human, combine it with automation, and we elevate the total productivity. So that's an example way back in 1850 of where we were starting to use automation to improve productivity.
Right. And so, you know, as the example of using a sewing machine as a very involved piece of technology to benefit and increase the output of a assembly line. Similarly, and around the same time is when we started to see the first dishwashers come out. Right. So in 1850, there were patents by Josephine Cochrane, who was developing a dishwasher via hand cranking. So the power of the dishwasher actually came from a human involvement. But it wasn't until the 1920s when the first electromechanical dishwasher was developed and started to gain popularity. And it was through the invention of these automated processes using electromechanical systems where we start to really see automation start to break ground in the early 19th century.
Could you imagine you and your brothers and sister having to, wash the dishes by turning a hand crank?
No, I could not. Not at all.
It was hard enough to get them to load the dishwasher.
Right, exactly. But then through the development of some of these more appliance type pieces, we started to get these ideas of what we're showing here as Unimate. Unimate is the first robotic arm design, and it was traditionally powered all via hydraulic systems. So there's not necessarily any electric motors that have been developed at this point, but essentially on a production line for things that are being casted, like casted metal parts, traditionally the workers had to wait for those parts to cool down.
Yeah, they got very hot, right?
Very hot, yeah, through the smelting and furnace process. And they actually developed this Unimate arm to remove those materials from ovens and then put them back on the line. And what this did was actually expedited the process of this assembly line via not waiting for parts to cool down. You have a mechanism to actually handle that stuff.
And you'll see another way that automation helps. It also, when things are very hot, they're also very dangerous.
Right.
And so the robot was, in a way, with a piece of automation, to use our term, was sort of keeping people away from that potential pain point.
Exactly. And then in the 1970s, Kawasaki and Unimate partnered together to actually create this line or this robotic arm at full production to be used in facilities. And then taking that technology to the next step, right? If you could imagine that the hydraulic arm is a very stationary object inside an assembly line. So then we talk about Shakey the robot. This came out.
That's my favorite name of any robot, by the way.
No, it's a pretty good one. And it came out in the 70s, and it was an experimental project by Stanford. And this is what we start to recognize as the first AMR, autonomous mobile robot. And this is a very important step, although it hasn't gotten much attention since then, since its first development. It marks the first attempt at making a mobile robot. And then we lead that into what we see in the modern age, the industrial robots.
Yeah, well, this is my world. But I think it's important to kind of illuminate the topic that we keep talking about, right? Is the idea that we have a market problem. And then we have scientists that are working in a lab like Shakey at Stanford. And then we have designers and engineers that ultimately package that machine. And that's kind of how we step forward through the history of robotics. So the next phase was really started in the kind of mid 70s. There's a German company called KUKA, and they had kind of transitioned the arm away from the hydraulics and into electromotors design. There's a lot of benefits that came along with that. At the same time, KUKA did it. There was a group at MIT that had created one at Stanford that had created one. And then now the current global leader, Fanuc, which is a Japanese robot manufacturer, they also started around the same time. And so these tools were starting to allow basically automotive manufacturing to accelerate, right? Having worked in the automotive world for a long time, is the margins on cars are very thin, the competition is very high. And so any opportunity that you could use to leverage your efficiency to improve your processes was something they were looking for. And so a lot of that science then was now being developed around these robots in order to increase their productivity. The 1980s showed a tremendous boost and increase in its productivity. The designs got smaller, they got better, the motors got better. We added encoders onto the arms, which we'll talk about later, so that the precision was also better. So not only were you getting more work, you were getting faster work, but you were getting higher quality work. And that was really what accelerated it through the time.
Yes, but in your experience, did you see these robots moving car frames around a manufacturing plant?
We didn't. No, actually, what we saw was the beginnings of the AMR, right? So the technology that was developed at the Stanford facility was actually was able to be used in what we called AGVs, which is an automated guided vehicle. But to the point is, they're nowhere near as advanced as the current AMRs.
Right. Yeah, but nonetheless, these robots were moving very heavy items around the facility at very high speeds. So what did we have to do? We had to put these machines in cages to actually protect operators from being in harm's way while the robots were actually functioning.
Certainly. No, that's a big deal. And the way that we've done that traditionally is that we'll take the robots and then we'll sort of put them in a guarded off area. Right. And we would use sort of aluminum fencing or steel fencing. And in so doing, we would keep the people and the robots away from each other. We would even use these, we still do today, these fancy laser systems that you would see in like a bank heist film, where it's looking to detect human presence. And we still do that today.
Right.
But the challenge with that is even as the microprocessors have developed and they've gotten much better, which is really kind of the early 2000s, the microprocessing capacity went way up. The problem was that robots were restricted to these cages.
Right.
And, having talked to a few in my years, they didn't like those cages. But the market demanded more use for these robots. They wanted to use them in other places, but we needed to address some technological concerns. And so we invented the cobot. And I think we should take deep pride, at least us from Illinois, that this was the development was begun at Northwestern University in Chicago, Illinois. But it was the idea of taking these powerful industrial robots that were typically made out of steel with powerful motors and that moved really quick, and make them safe for people to be around, basically to let them out of their cage and sing. So what we did is the scientists and the engineers developed the process of the cobot, which basically derated the force output torque of the motors, limited its speed, and then this is really where the magic started to happen is and Andy's going to dive into this, but the development of very sophisticated sensors so that the robots themselves could have some sense of what was in their environment. So if they were going to make a collision with a human being, they would know that ahead of time and redirect their path. And so that technology, coupled with the advancement of the AMR, which compared to Shakey, our friend, is far more advanced now. And Andy will get into the reasons why that is the case. But basically, marrying the cobot and the AMR together is really what has brought us into what we would call the service robot world. So as you can see, the service robot world, service robot itself is really just a natural extension of both technology and market demand coming together to create a tool that people use. This, to me, these service robots that are in the market today are much more like dishwashers and washing machines. They are very simplified systems that do a lot of complex things, but they do it pretty much all under the hood.
Right. And as you can see, kind of this evolution of the robotics, the service robot is now the extension of all the tech that went into the industrial robotics, all the tech that went into cobots and the AMRs, and now we're simplifying the task, simplifying the operational usage of the machine, and lowering the barrier of entry for people to actually implement and install this equipment. For industrial robots and cobots, typically teams of engineers spend weeks and months getting those robots to do the processes that they need to. But now with these service robots, the technology is allowing much easier usage for just the general public and people who don't have that engineering background. And that leads us into our next topic of the human-robot interaction. And we can see Pepper down here, but the human-robot interaction is a field of robotics that is describing how humans actually interact with the robot. It doesn't necessarily mean humanoid, although that is a progression of this technology. It more accurately describes what someone would do with the robot, how to make it do its tasks, how do you service it, and how do you just interact with it in general.
Yeah, and we'll get into more detail on that later.
Right. Well, why now?
Yeah, and I think that's a great question. And that's something that Andy and I had kind of talked about it. I mean, one of the reasons that we're excited to participate in this environment is that, the time is different. It's changed. And we kind of see it as the combination of two really powerful forces. And one of the things that's just a basic reality is that the world has got more complicated. There's a lot more opportunities for our young people to build careers that are non-traditional, whether that's in social media, whether that's in computer engineering, whether that's actually even in participating in the gig economy. And what that's really created was a vacuum in a space. Traditional jobs that people used to go into and make their careers are now being left empty. Right. And what we're seeing is there's people from all over the world that are struggling to fill these, sort of jobs that, in many ways people just don't want to do. Right. They don't engage their personality. They don't give them a sense of agency or purpose. So that power of that demand, I think, mixed with what Andy's going to jump into here soon, is the increased sensor reliability, the improved computational speed, the advancement in motor control to allow for more accurate and controlled motion, and then the increased level of safety. So it's the technological push we just talked about, coupled with the market demand for these things, that is creating a powerful tailwind behind these tools that are making it much easier for people to choose to solve some of their more complicated problems.
Exactly. And it's that level of safety that is making people more comfortable with the idea of this technology. So what is a service robot?
What is a service robot? A service robot is a device, right? That if we wanted to sort of go with the World Robotics definition of that, they would say a service robot is an actuated mechanism with programmable degrees of freedom that can move within the environment and perform useful tasks, excluding industrial applications. So what does that mean exactly?
Right.
The idea is this, as we've been describing, is the next step in the automation space, past industrial automation. Service robots basically have escaped the factory. They've escaped their cages. They can work with people in the environment. We have the D-rated motors. We have force limiting. We have the improvement of the sensor technology. And then we have compact, simplified tasks. So basically what a service robot is taking all the technologies that we have, marrying it with the market demand to do very simple tasks in a way that they've never been done before. So that's what a service robot is. Would you agree?
I would agree entirely on that. So what kind of service robots are there? What are the categories?
Yeah, so it's a great question. So what we've been talking about a lot around is about service robots, what they are, that they're this evolution of technology. But then the question is, what can we do with them? And there's going to be, you know, one of the jokes that I hear a lot is when I tell people the business we're in, they're like, hey, do you have a robot that can fold my laundry? Or do you have a robot that can come, clean out my garage? And while we're not there yet, right, and who knows if we ever will be, there are certain tasks that we've kind of, as a market or a society, have come to the conclusion where service robots fit. So one of those is process. We kind of describe it as a process group. And what that is machines that already exist in our environment, right, but that are proven processes like vacuuming or scrubbing. I mean, some of you may have a Roomba or an iRock, or we have a Eufy, because and so these are proven systems, and all we're really doing is putting them on an AMR, right? So we're taking a proven process mechanism, putting it on an AMR, and it's able to autonomously move around. So that's one type of thing. We also have the security, which I think is interesting, where you have security cameras all over the place, and all this is taking all of that equipment, putting it onto an AMR, which we've been talking about, an automated mobile robot, and it can move around its environment. Right. So again, these are attainable things. And so these are the first areas we've gone to as a market, as a technology. The second one is sort of delivery robots, which is kind of built around an idea that I've kind of thought about for a long time, being in the automation space, and that's the idea of waste motion. So when you're talking about manufacturing and trying to improve processes, one of the things that you're trying to do is to eliminate the waste motion, right? Okay. Motion that humans behave that don't necessarily add value to the process. And that's really where service robots have come into play big time. So basically what they do is they just move things from point to point. There's a lot of wasted time, like whether in a restaurant, getting food from the kitchen to the table, or the dirty dishes to the cleaner, or in a factory from the warehouse shelves to the shipping department, or between processes. So the delivery robots are basically AMRs with the ability to take out that waste motion. So those are really the areas that I think the technology has really proven that it's very reliable and effective.
Right. Absolutely.
Now it's time to turn it over to the brains of the operation. Time to go under the hood and let's figure out how these things actually work.
Right. So what's going on inside these service robots that are allowing them to do the jobs that they can do? Firstly, we're going to talk about algorithms, right? What is an algorithm? We've heard this word before. People throw it around a lot. But essentially, it just takes inputs, runs them through a mathematical system and process of steps, and provides one or more outputs. All it is an input-output machine. So an algorithm is just going to take some sensor data, more than likely, and run it through a series of calculations and processes such that it makes sense of this data, so it can produce an output that's useful. And that's all it's doing.
Yeah.
And we're going to talk about artificial intelligence, which is just types of algorithms that do certain processes.
Yeah, and I like to think of algorithms as kind of the magic, right? This is where all the magic that the modern world is really built around. But for a layman, like myself, in terms of the deeper levels of the engineering, it's a lot like an Excel spreadsheet, right? So if you ever built an Excel spreadsheet and you're looking to get a value and you create a formula, and then you've got a series of cells that feed into that formula, by changing the values in those cells changes the output. So the formula really is an algorithm. Right. So you take inputs, and based on those inputs, it changes an output. So sometimes that's an easier way to look at it.
No, that's a very good example of how these things work. 100%. So then artificial intelligence, the biggest buzzword that we're experiencing right now, whether it's through media, through the news, or just through casual conversation. What is artificial intelligence? So on the left, we got a description for it. But essentially what artificial intelligence is, it's our umbrella It's the overarching category that describes all these separate algorithms that do very specific processes. So something that might be thrown around in the same conversations is machine learning. And machine learning is actually the foundation where a lot of these algorithms are built out of, because what it describes is it describes a learning network, also known as a neural network. And these are these are the patterns that the computers and that these algorithms are putting in place and tombstoning in a way such that every single time new data comes through, it runs through this network and produces this output. In the same category are GPTs, which stands for Generative Pre-trained Transformers. And that's what ChatGPT is. It's doing is it's relating the information that you're putting into it, and it's running through basically a pattern recognition network, and it's generating the most likely outcome that would follow your input. And that's all it's doing. It's just predicting what's supposed to come next, right? Computer vision is another overarching category of artificial intelligence algorithms that allow these computers and these robots to see the world, right? Image processing network. This is how we're doing our object detection, our object recognition, right? And then we feed that information to our path finding and our path planning to do object avoidance. And you can see that there's this process of where this information travels in order to make purposeful actions, right? SLAM. SLAM is something we're going to talk about quite a bit. It is more of the foundation for these service robots to actually create an environment and put itself in that environment. It stands for simultaneous localization and mapping. And that's what it means. It is at the same time, it's mapping my environment and putting myself in that environment.
It's almost like it's creating a 3D world in its head.
Exactly. It is creating a virtual world that
virtual 3D world.
That it can navigate. It's using these supplementary sensors to verify that environment. And then we have robotics and autonomous systems, which is another category of these algorithms that pertain explicitly to service robotics. Pathfinding, like I mentioned earlier, this is part of our object avoidance. So using that image processing network, we can plan where we're going to go based on the objects in our surrounding. Planning and control. A lot of these robots work very well in tandem with other versions of themselves, right? So I could have 3 units, 4 units in one area, and they're all communicating with each other, planning, the routes they're going to take, and fleet organizing, essentially. And then sensor fusion is something we're going to talk a bit about as well. And that's just marrying all this data from all these fancy sensors into a set of processes, an algorithm that is able to make purposeful actions. So it's making data useful is really what our sensor fusion is doing.
100%.
Right. So now that we've kind of established what artificial intelligence is, right, and using these algorithms to make actions that mean something based on our data, where do we get this data from?
Yeah, right. We got to get the data. In order for the algorithms to work, we need data.
Exactly. So we're going to talk now about our core hardware components. So these are a lot of our sensors, right? So we can break them down into our vision, our optics, right?
Is anyone surprised that he started with the optics?
Nope, not surprised.
I wasn't surprised.
We're going to start. We can start with talking about our optics, our LiDAR, our RGBD, time of flight, structured lighting, and stereo vision. All of these are sensor types and sensor techniques to actually obtain information about our environments. And then we have some of our supplementary sensor devices like wheel encoders or ultrasonic sensors, bumper sensors, microphones. These are also feeding into that sensor fusion algorithm to make data useful, right? And we're going to talk about CPUs, GPUs, and IMUs, which is a new term for a lot of us. Chassis design, the touch screen that allows operators to interface with the service robotics parameters. And then our motors. How do we actually propel this robot in an environment? How do we stop it? And how do we measure how far we're going? Right. So we're going to begin with the optics and the optical components. These are our eyes and that allow these service robots to see the world.
Right. It's what kind of takes this old industrial robot and brings it into the world, right? In order for it to move around, we've got to let it learn what the world looks like.
Right. And that's a great point. For most of the time of industrial robotics, if you're thinking about imagining the world from their point of view,
Yeah.
they're in the dark. They have no idea what's happening, and they're just following a set of protocols.
Correct.
Whereas now we're giving them that environment data.
Yeah, and if there's a steel I-beam in its way, it plows right through the steel I-beam in the industrial space.
Right. Optical sensors.
Yeah.
LiDAR. What is LiDAR? You've heard this term before when Google cars were mapping the roads or Waymo or Tesla not using LiDAR, right? But it stands for light detection and ranging. Radar, radio detection and ranging, and then there's sonar, sound, navigation, and ranging. These are all time of flight technologies. So essentially, I'm sending out a laser pulse, and I'm timing how long it takes for that to come back. Okay, and that's based on a very simple velocity equation. The speed of light is constant, and that's why we're able to do this.
And I was going to say, this is the thing that kind of blows my mind is when we were talking about this, that the speed of light is what, 3 times 10 to the 8th meters per second?
Yes, 3 times 10 to the 8th meters per second.
All right, well, can we explain that, what that means to regular people like us?
That's 620 million miles an hour. And that is an unbelievable speed, but it's also a constant speed. And it's actually interesting why that is a constant speed, but if you want to ask, I can tell you about that
later.
But the LiDAR, it is sending out a laser pulse, and it's measuring how long it takes to come back. And it's sending out hundreds of thousands of pulses per second. So we're able to create an image of our environment very quickly. Because I'm measuring the time, I can determine how far an object is away from me. And then doing that, I can actually create a map of my environment and the walls that are constraining where the robot will move. And this is controlled via mirrors inside a laser system. And it just sweeps that laser around both this way, and it'll go ahead and create, that environment for you. And then we have our RGBD sensors. So this is a sensor package, right? We have a typical camera in there, like same sensors that are in our phones and our traditional cameras. And then that's coupled with a depth sensor. And depth sensors come in a variety of ways. The most traditional for both cost and accuracy is a time of flight sensor. And this is very similar to LiDAR. LiDAR uses a laser, and this time of flight sensor uses a source. And a good way to think about this is if you're watering your flowers out in your garden, and you put your hose on shower mode. So shower mode, it's going to spread all that water out into a big area, versus jet mode, which would send all that same water out over a longer distance in a finer column of water stream. So that's the difference between the time of flight and a LiDAR system. Structured light projection techniques. This is an interesting one, as an infrared pattern is projected onto the environment. And there's very rigorous and robust mathematical calculations that allow that pattern's distortion on the environment to create curvature. And then there's stereo vision. That's actually how our eyes work, right? We have 2 different imagers, right? Cameras that are creating 2D images from 2 different perspectives.
Which now you understand why life as a pirate is so difficult.
Right, exactly. But stereo vision will allow 2 different perceptions to create depth. And this contributes largely to our object avoidance and object recognition, but also part of our map verification, right? Because we're using all these sensors have errors, and we need to validate our data via other sensing techniques.
So would you say using both of these technologies, sort of fusing them together, improves the accuracy of what the robot's actually seeing?
Without a doubt.
Okay.
None of these can be used alone to produce as accurate information as is available on these service robots.
That makes sense.
Yes. Great. So we have our data from our optical sensors, and now we need to do something with it. Making data useful and actions intentional. So as stated earlier, our computer vision is our overarching category that gives these optical sensors much more capabilities and allows that information to be acted upon. SLAM, as mentioned earlier, is our simultaneous localization and mapping. Like stated, imagine being in a dark room and someone asks you, what does the room look like? And where are you with respect to the wall? That's a very difficult problem to solve. So that's what SLAM is doing. It is creating our environment while at the same time putting ourselves in that environment.
And it's doing that by taking the information from the LiDAR and the RGBD, correct?
Yes, that
Yep.
and the other sensors available.
And the other sensors that are on there, yeah.
Right. So a big part of SLAM is actually the wheel encoders that are on the wheels.
Yep.
So it's measuring how many steps we're taking, essentially.
Okay.
And then image processing. This is how our RGBD sensors and our cameras are detecting objects and then using that information to make purposeful actions to avoid. And this is largely due to our RGBD sensors and the supplementary cameras available.
Okay.
What other hardware components kind of go into the optical sensing that allows these robots to move? And we'll go over a brief overview of some of these systems because we'll get into them. But we have wheel encoders that are counting our steps, active cooling. So any computer that you've ever interacted with, you can hear the fan. And all of these robots, or all technology in a way, right, needs to be actively cooled. Chassis design. How does an operator interact with this unit? How does someone maintain the unit? And how does someone build the unit, right? This is our chassis design.
Kind of like the foundation of the mechanical system.
Exactly. Yeah. Right. It's the difference between a Windows computer and a Mac computer is that chassis design, right? No,
we all know the Mac is better.
All right. Our IMU, our inertial measurement unit, our GPU, our graphics processing unit.
And I just want to jump in. So from a GPU perspective, those of you who are smart enough to invest in NVIDIA, I wasn't, NVIDIA actually makes GPUs. And the reason that their company is, sort of going through what it's going through in terms of growth is because of the global market demand for GPUs. So
right. And I'll explain why that is.
We'll talk about that later.
And then our CPU, or central processing unit, basically controls our main interface. Ultrasonic sensors used for object presence detection, not object dimensional detection. Touch screens, which is the main interface for the operator and the machine. A battery. These service robots are very cool, right? But if they run for an hour, how useful is that? So the battery technology making these robots perform tasks longer, right?
Right, and an AMR shouldn't be dragging a plug around.
Right, and you don't want to plug it into the wall and get it all tangled in the wheels. But that brings us to our wheels, our motor designs, our drivetrains, our suspensions, right? How are we propelling this service robot through the environment, and how are we protecting our cargo? The embedded controller board. This is a main difference between industrial robotics and service robotics. And that's because in industrial systems, the controller boards are always external.
Correct.
Right? Either outside the cage or completely external to the arm itself. But for the same reason of the battery and dragging around a cord, we needed to put the embedded controller board onto the machine, such that everything is housed into a single unit. And then we have bumper and haptic sensors, which are our last line of defense in the event that some of these other optical sensors fail in some of the ultrasonics. But this is a physical interaction with the environment that is telling the robot something.
Correct. But as we talked about the derating of the motors and things of that nature, it's not unsafe. It's really more to protect the robot itself.
Exactly. Yep. Right. And then our microphones and our speakers, which are our audio interaction with these service robotics. So let's talk about the wheels. Yeah. Right. The mechanics behind.
Can't have an AMR without wheels.
Right. The mechanics behind the movement. Right. The motors. Right. So there's several types of motor technology. Typically in service robotics, you'll see stepper motors a lot more because they are different than the brushless DC, because the brushless DC just spins and the stepper moves to a position. And the positional accuracy in tandem with the cost of these motors are very attractive towards the building of service robotics.
Yeah, and to give you some perspective, like stepper motors are used in copier machines. They are used in all sorts of what I would call appliance type products because of their low cost of manufacturing, but added value of the precision, knowing where they're at all times. And that is very important, specifically in a robot.
Exactly. And then we'll talk about the suspension, right? How do we maintain, in let's say a restaurant scenario, how do you deliver liquids without them spilling, without dropping stuff? And a lot of these systems are custom built suspensions, active dampening, that would be an optical sensor feeding data to the suspension system to readily dampen the movement that's about to come.
And wouldn't you kind of That's a lot like a car, wouldn't it? I mean,
It's almost exactly like a car.
Yep.
Whereas, our cars had that suspension system, giving us a smoother ride. And then our brakes, right? We need to stop this service robot while it's moving in the environment from either hitting things, or when it sees an obstacle, it needs to stop, right? And we want to protect our cargo while that happens. So regenerative braking, like the Teslas, DC injection, right? Using a magnetic field to stop the rotors. But essentially, these are all electromagnetic principles that are just allowing these motors to gradually stop. And there's nothing that is very abrupt in that transition. And then our wheel encoders, right? All the wheels have encoders. And what this is, it's just counting steps.
Yep.
Very similar to our car that's counting our mileage as we continue to drive. It's an odometry technique that's actually being used in the SLAM algorithm.
it's also for old people like me who need to make sure that I move. So I count steps on my watch.
Exactly. Right. So by turning rotational motion into signal, we're able to use that in our SLAM algorithm and actually allow for more accurate positioning.
Right.
And then our control, the sensor fusion, the active learning within the environment. This is our magic steering wheel that's allowing us to navigate our environment safely and reasonably.
So using the word magic in my world, right? Even someone who's been around for as long as I have, this is really the magic. This is really where the art of what we're doing is going to happen. And this is really what allows the complexity to kind of be taken away from the individual user. So why don't you kind of talk us through what all these letters mean?
Right, all these letters. I mentioned the inertial measurement unit, and this is a combination of accelerometers, gyroscopes, and magnetometers that are being used to verify the movement of the robot, so that the SLAM algorithms and the sensor fusion algorithms have much more accurate data to act upon. And it's really just a verification mechanism. So similar in your Apple Watch, when you flick your arm up and you look at it, the screen turns on. That's an accelerometer telling the CPU and the control mechanisms that I need to initiate my next command, right? And that's what the IMU is doing. Mm-hmm. It's using these accelerometers for, to measure acceleration, gyroscopes to measure orientation, and the magnetometers to measure direction, comparing that to magnetic north for the Earth. It's able to validate all of its data and create these environments very accurately.
So would you say that's kind of another sensor?
It is absolutely another sensor. Yeah, 100%.
And it kind of goes to the idea that the more sensor input data we get, the better sort of the outcome we're likely to have.
Exactly.
Okay.
Right. And then our CPU, or central processing unit, this is the main interface with the screen and the buttons, and in traditional electronics, it's the main brain for the device. But as Ryan has mentioned, GPUs are becoming much more popular, especially as artificial intelligence starts to gain traction. And that's because a GPU is a very special CPU designed for small calculations and relating data points together. And that's what an algorithm is doing. Mm-hmm. Small calculations that are relating data together. Mm-hmm. So that's why the GPU is the main structure that's running the complicated algorithms that we call artificial intelligence. Mm-hmm. And that's where all that's happening. So these three units would be on that embedded controller board that's inside the machine. So it's the motherboard, the battery, sensor package. It's where all the communication happens. It's like the main hub for data and actionable items.
Yep. And to tie this back to our original conversation, right? This is the end result of a century's worth of scientific discovery, engineering, and design, right? We're now at the place where we can take all this information from all these sensors, run it through these, very advanced microprocessors that can handle all that data and then translate that into an output that is desired, which in our world means a robot that works.
Exactly.
Right.
100%. Okay. This is where all of the sauce and all the ingredients come together to make a purposeful unit and a beneficial unit. What is this human-robot interaction? Like, how do we take all of that sensor data, all that movement, and how we start tying in people and how they interact with it?
Right. And so the idea is we still love people, right? I mean, as a culture, as a society, right? And so if we're trying to unburden our people from doing the tasks that they're not interested in doing anymore, or they have, just not an area that they want to sort of create their career, we're going to use these tools the tools and the humans in the service robot are going to be working together. And so one of the things that's important is how do we construct systems where the humans can interact with the robot itself. And so one of the ways is a touchscreen. So most of us are familiar with touchscreens. They're on the phones in our pockets. But robots will oftentimes have service robots will oftentimes have touchscreens so that you can interact by modifying the parameters. If you want to change the speed, if you want to change the route, if you want to, take that virtual world that it created in its head and make changes to it or edit it, take out some noise if something was there you didn't anticipate. We use the touchscreen for that. We also have microphones, and this allows humans to speak directly to the robot. And now, while that's still somewhat in its early stages, you see examples of where people are, using it today with some measures of success. And then you have a speaker, and this is the chance for the robot to talk back to you,
Right.
and to share with you, information that you might be looking for where you don't have to read it. And so that comes, where the speakers really come into play with this. And then
Yeah, and then the chassis design is where, that's where the actual physical interaction begins. How easy is it to interact with it? How easy is it to operate? And how easy is it to maintain from a maintenance perspective? That's where the chassis design really becomes important.
good point.
Right? Because we can design very cool, technology and objects, but if we can't freely interact with them, how useful are they? Right? But then taking that to the next step, right? And we start talking about these algorithms.
Yeah.
We might be able to speak to the robot, but how well can it pick up what I'm saying? Right. And that's when we start talking about speak to text, the LLMs and the GPTs that start to become much more useful in that interaction.
Yeah.
Whereas we have these algorithms to actually supplement function, but now we have algorithms to supplement interaction. And that's where a lot of the finesse starts to come in when you're designing these service robots.
You can see these algorithms aren't going anywhere.
Right.
They're very useful, right? They're very useful.
And then our object detection. This is how, the robot continues to interact with the environment and with the humans in that environment. Right. So taking this human robot interaction, we're going to start talking about the connectivity and the back end that's going on behind the scenes that makes these things much more useful.
Yeah, and you might imagine this is sort of the next phase of the service robot is, well, I don't want to steal Andy's thunder, but it's an important sort of next step that, again, leverages technology that has been, continually developing over the last, 40 to 50 years.
Right. And that includes our cloud-based fleet control, right? We can have a robot conduct capabilities and functions, but if we want to introduce another service robot to that environment, how do they talk to each other? How do they become more of an efficient unit?
Sure.
Right. And that's where this fleet control comes into play, where these robots can talk, plan, and then operate in unison in multiple parts of an environment.
Right. This reminds me of when I used to take the kids out and we'd try to do something in the yard. And I really could have used some fleet management when it came to that, because I don't think we were very efficient.
No, that's a good point. And then we want to start talking about our supporting applications and our software. How easy is it from a operator point of view to actually code or program at a high level with low barrier of entry, right?
Right.
And that's where the finesse of creating these applications and software really start to really show their true colors. Is how easy is it to really operate this machine from a coding or background point of view? And then,
well, I was going to say the other thing is one of the benefits too is, like in our business, we've if there was a time when we didn't have this remote connectivity, which I know, the ability to upgrade software remotely,
Right.
and so that again, there was another waste motion function eliminated. We used to have to send technicians from Chicago to Keokuk, Iowa, or to Fort Lauderdale, Florida, to fix a machine.
Right.
Well, now because we can connect to it remotely, right, all of that time and cost of flying back and forth has now been saved. So a service robot of a kind.
No, exactly. I mean, servicing service robots is very much an art, as well as much as a technological field.
Yeah.
Right. Because to your point, if you had to go, on a 3-hour drive to go see what was wrong,
Correct,
prior to, having that knowledge beforehand, you could save yourself a trip or two.
Yes, which makes your total expenses lower, which, makes your operational efficiency better.
Right. Absolutely. So where are these being used? And they're traditionally being used right now, as described earlier, those processes, right? cleaning is a very robust process that can be put on an AMR, and you can use, that service robot to conduct large format cleaning. So that, yeah, so commercial floor cleaning is an avenue. Restaurant delivery, right? Using it to deliver food items to tables, dishes back to the dishwasher, as well as warehouse or manufacturing delivery for parts, right? And then there's that waypoint guidance, right? Imagine being in a big mall or a big museum and you don't know where to go, right? You can walk up to a kiosk, you can take a picture of it and walk on your phone as you travel through the museum, or you can utilize some of these concierge robots.
Yes, got an AMR.
Kiosk on an AMR,
Basically,
exactly,
right?
right.
I mean, at the end of the day.
So that's where some of these robots are being used and tested out today. But with the advancements of where these things will go, the capabilities become much more high level instead of being, just floor cleaning or just waypoint guidance.
Correct.
There's going to be an evolution to these machines as well.
Yep.
But where does that evolution come from?
So as we're wont to say at times, and we heard it somewhere, I don't remember where, but this is the worst robots will ever be. And what we mean by that is referencing that history conversation that we had earlier, is that, technology just keeps building.
Yeah.
And what does that mean? We're going to get faster processing units. So we're going to be able to take in more sensor data. We're going to be able to process it with faster microprocessors. And ultimately, it's going to end up in better performance.
Right.
And so one of the cool things that we like to talk about in terms of where the future is going, the future is going where the market decides it's going to go. And what we're seeing is the market wants automation. People want more time to focus on the things that they care more about. And that gives them that sense of purpose and sort of wholeness of living. And so where we expect the future of service robotics to go is to go into any of those areas that, jobs that people just don't really want to do anymore, and that actually help us in ways that, it is difficult for a human to help. So it's only going to get better from here. And we're very excited. We're excited to be a part of it, to live in this environment. It's something that we've cared about a lot, but we think the future is only going to get better.
Right. No, exactly. Algorithms will improve, right? Faster speeds, safer metrics, more can be done.
Yes.
Right.
Yes.
So this is a great time to just ask any questions. Either drop them in the chat or just go ahead and unmute yourself and ask.
Yes. And excuse our lawnmower in the background if you can hear it. So we didn't expect that part. Right. But yeah, go ahead and unmute yourself and ask some questions, please.
Hi, Andrew and Ryan. This is Sam from Fairfax, Virginia.
Hi, Sam.
Great presentation. Thank you for the information. I know you guys mentioned about the industrial robots having different components, outside the robot itself. Given the motor, the encoder, the driver, and the controller. So how were we able to fit all these components inside the service robots? I haven't looked at the the service robots yet because I haven't received them, but just I know the analog signal have to be converted into digital for the controllers to understand where all this motions and speed, all that is coming from. So do we have each encoder for each signals, or I don't know how it works? And
Right.
Look at it.
Yeah, no, good question. Do you want to take this one?
Yeah. So just to create a distinction between the industrial robots and the service. So the motors on those industrial robots, they're much more powerful and much more technologically developed versus like the motors inside the wheels propelling the service robots through an environment.
Right. For an example, like we have servo motors and industrial robots that have 64 million counts every time it rotates 360 degrees. So
Right.
very highly advanced. Whereas in these particular units, they're not quite as advanced.
But that's what allowed the service robots to actually take all this technology on board. It's because in some respects it does have simpler technology, but at the same time, the industrial robot needs to operate within a volume. So like if I could imagine the industrial robot in a cage on a table, it's got to be able to access most of those, if not all of those points on that table. So putting those embedded controller boards and some of those other sensing technology on board the arm is going to provide space issues,
Correct,
and operational issues. Whereas the service robot conducting those simple tasks will you'll have more freedom in the environment to operate that robot, and also more freedom in the design to put some of these components inside the machine themselves. But most of the motors most of the motors nowadays have encoders built into them.
Yeah, I would say it is very, I mean, yeah, it is unusual in anything that would be described in automation that would not have an encoder in the motor. And so to your point is, we do encoder counting in a wide variety of ways. A lot of times it's really just pulse counting at this point. The use of analog, is not used as much as it used to be. But the continual advancement of the science and the engineering has sort of gotten to the point where these are just so small. We've are manufacturing these sensors, and encoder really is a sensor at scale. And so in terms of the service robots, they've just gotten to a maturity level to where the cost and the technology have gotten to the point where it just is capable of being used in such a dynamic application.
Right.
Awesome. Thank you so much.
Thank you. We appreciate you.
Just one last thing, from the futuristic point of view, I know in your last presentation you showed a robot with an arm. Right now, the limitation that we see with the service robots to become a fully AMR, like the industrial robots, are the pick and place kind of thing. So we're only focusing on motion at this point. But do you think that's coming anytime soon, where that will fully automate that service robots, even pressing the robot, instead of upgrading the elevators, just pressing the with the arm, calling the elevators and stuff like that, or picking and placing objects?
Yeah, without a doubt.
So if you think about that image that we showed you guys in the evolution, I don't know if you can go back to that, in the evolution of robots. No, this is not the one I wanted. Is that all what you described is, I don't want to say old technology, but available technology, right? If you remember this slide here and this guy, at the end of the day, that's an AMR with a cobot on it, right? And it's a single arm cobot. All this really is here, if I can get back to this other spot, what am I doing wrong? All this other one here that you saw in the picture was an AMR with two arms.
Right.
And once he gets back to it, I want to show you guys this real quick. But sorry, we're new to this webinar field. Okay, so this guy here is real. All that really is an AMR with two cobot arms.
Yeah.
And so that technology is accessible, right? The question is, can you do it in a way that is cost effective?
Right.
That is effective. Cobots sometimes have limited force compared to the other robotic arms, as we talked about. Is an intentional thing. But yeah, no, we certainly, I believe that thing on the right is a product that is coming near commercial viability. So yeah, we think it's coming very soon.
The main thing to balance is the cost. When it comes to the arms and the pick and place, they're just more costly technology. Whereas the motor and a cart system, a smart cart system, can be manufactured at a much lower cost than any kind of cobot arms. And that's kind of where the real barrier is at the moment, is trying to develop this arm technology to be cost effective enough while also producing what you need it to do.
Yeah, for it to still be useful, right? And that's always the struggle that design and engineering has, is this struggle between functionality, cost, and sort of ease of manufacturing and robust and reliability.
But without a doubt, that is the next step of these service robots, is to give them more augmentation with their ability to manipulate objects.
Yeah.
Awesome. Thank you again. Great.
Right. Thank you. We appreciate the questions. We love questions. So.
Yes. But there's more time for questions if you guys want. But here's our contact information. Whether you want to contact us via email or call us or follow the socials, but ready to answer anything that you guys might want to throw at us.
Yeah, and we're here to help. I mean, that's kind of the way we look at the world is, we like automation of robots because it helps people. And so even if you just want to have a further explanation, or there's an opportunity we can answer some questions, or you'd like to see a service robot in real life, feel free to reach out to us, and we're here to help in any way we can. So,
right.
All right.
So thank you for coming. We
you.
really appreciate that, and I hope this was informative and at least helps you frame your understanding around robots, service robots, and kind of where the markets are taking this technology.
Yep. We really appreciate your time. We know how important it is. So we hope you enjoy the weekend, and hopefully we'll reconnect at some point in the future.
Awesome. Thank you, everybody.
Thank you, everyone.